Hi, this is exercise 1D, another lesson on matrices. So we saw last time how to find the determinant of a 2 by 2 matrix. And this lesson we're going to learn how to find the inverse of a 2 by 2 matrix. And the two are linked, definitely linked. So let's get on and have a look. Now first of all, I've got a starter for you. Last time I asked you to try and make sure you could type these into your calculator. It doesn't matter which type of calculator it is. But this one's a times, this one's an add, or this one's another times. So just practice, see if you get the right answer. You'll know. You can, for instance, this. You can work this out easily enough in your head. But the others, these are a bit harder. So have a go for it. Those are the answers. And your job is to make sure you get the same answer on your calculator. Now anyway, the inverse of a 2 by 2 matrix. So there's a simple method for doing this. It involves the determinant. You'll notice I've got a rule here. It says if M is A, B, C, D, then the M inverse is 1 divided by the determinant of M times by, now look, this seems like a random order, but really what happens is you switch these two around. And remember last time talking about it's all about diagonals with 2 by 2 matrices, and the A and the D become D and an A, and the B and C, well, they are in the same places, but they just become minus versions. So these just switch to being minuses. So copy down that rule that if M is A, B, C, D, then M inverse. Notice this is, it looks like a power, but we've seen at GCSE that sometimes you write to the -1 and it's the inverse. You might recall writing functions. A function in GCSE was written as f of x, but you might also recall that you had to find the inverse of a function, and that was always written f inverse like that, and that little -1 meant inverse. It's the same here. So the notation is a bit weird, but you just got to get used to the fact that in different settings in mathematics, some notation is sort of reused and repackaged. Anyway, so if I was asked to find the inverse of this matrix, the very first thing I'd do is I'd find the determinant. Remember the formula is AD minus BC using this setup. So AD is 21. There it is. And 1, 5 is 5. So that's 16. That's an unusual number, but there you go, that's what it is. And so therefore, if I want to find the M inverse, I write 1 over that 16, and then I just, remember what I do, I switch the A and the D round, and it becomes DA, so I just nearly wrote D then. So it's the 3 and the 7 round in this case, that's 7 and 3. And the 1 and the 5 just become minuses. There it is. That's it. So what you take from that is you could rewrite this as 7/16 minus 1/16 minus 5/16. Notice that I used a word at the start that you could. It implies I wouldn't. I needed a bigger bracket. It just becomes really clumsy. So it's just easy just writing it like that. I'm just looking at that 1/16, 7 minus 1 minus 5, 3. I think it's exactly the same as I've written. Good. So here's another one. Perhaps pause the video, see if you can do that. Meanwhile, I'll do it now. So hopefully you pause it and you've got an answer. Otherwise, so what's the determinant? It's 10 minus. This is 6, and it's plus 6 when you do it. So it's actually 10 take away 6. I think that's 4. So my inverse, I'm just going to do it here. M inverse is 1/4. Notice you always just take the number, put 1 over it. Flip these two numbers, 5 and 2. Make these positive. Well, make them negative, but they're already negative, so they become positive. That's what I meant to say. And I think that's the answer. You could write that as 5 over 4, and 3 over 4, and 2 over 4, and 2 over 4, whatever. But notice you don't need to. Just write it as a number times by. Remember that last lesson we said that if a matrix has the determinant of 0, then this is called a singular matrix. A singular matrix. So here's a question. It says 8. If A equals 8, 1 minus 2A, 1A, find the inverse and state whether the inverse, when the inverse doesn't exist. So I mean, I'll just find the inverse first of all, and then I'll talk to you about why this is to do with singular matrices. So first of all, we've got, just notice we've got A's in there, which is a bit weird, but it's easy enough. We just do the same rule. A inverse. Well, I need to find the determinant. So what's the determinant? The determinant equals, what we do, we times those together. And then we take away this times by this as well, that diagonal. And that's times by 1, so that just sticks with that. So it's minus, or 1 minus 2a. Now I reckon that is minus and minus is a 10a minus 1. So therefore my determinant is 1 over 10a minus 1. We've not seen one like that before, have we? But then we do the same trick. We find this by switching the a and the 8 round. And the these thing here becomes minus, so that becomes a minus 1. Well, this is interesting. If I make this minus 1, and this would become a plus 2a, I might as well write it 2a minus 1. It's just an easy way of writing it. And that's the answer. And this is the bit I'm more interested in now. State when the inverse doesn't exist. Now notice, this won't exist if, see, this has a problem if I divide by 0. Whenever I divide by 0, there's a problem. You try it on your calculator, you're not allowed to divide by 0. 48 divided by 0 won't work, 12 divided by 0 doesn't work, 1 divided by 0 doesn't work. So therefore you can't divide by 0. So when 10a minus 1 equals 0, we will have a problem. Move the 1 over, 10a equals 1, a equals a tenth. So if a equals a tenth, there's no inverse. Oh, I don't know what happened with that funny line. So if a equals a tenth, there won't be an inverse. And that's basically what I've got here. I've written that down. I think it's exactly the... Oh, I've just realised that's been written wrong. That's definitely the wrong way around. I switched them. So this should have been 2a minus 1, and this should have been the minus 1. But other than that, it's right. You can see it's a relatively new question. But the critical thing for me is that it doesn't work when a is a tenth. So from that, we can take this idea that you can say if a matrix is singular, it doesn't have an inverse. It doesn't have an inverse, and that's just me writing the same thing really as I've got there, but just writing it in a slightly different way. So a bit of matrix algebra for you. Now notice here I want to solve this equation, and in order to solve this equation, effectively I've got to get x on its own, so I've got to move that matrix over there. Now in normal maths, if I had 3x equal 12, I'd just move the 3 over and I'd say x equals 4. And of course what I'm doing is I'm dividing both sides by 3. That's really what I'm doing. Now here I've already said to you I'm not allowed to divide by matrix. But what I can do, and this is the subtle trick here, is I can multiply both sides by this. And the reason why I'm saying this is if I start with 2, 1, 1, 1, and I times it by its inverse, and its inverse, whatever its inverse is, in fact let's just do its inverse now. Its inverse would be I switch these two round, 1, 2, I make these two minuses, and then I have to divide it, or effectively work out its determinant. What is its determinant? It's 2 take away, well that was lucky, its determinant is 1, so if I effectively times by 1 over 1 it will still be the same. So I was lucky there because I didn't really leave a space. But if I was to multiply these out, what I've said to you and hinted at to you in the past is that it gives you an interesting number. 2 times 1 is 2, 1 times minus 1 is minus 1, so I think when I add those together I get 1. 2 times minus 1 is minus 2, 1 times 2 is 2, I'll get 0. 1 times 1 is 1, 1 times minus 1 is minus 1. That will be 0 as well when I add them together. 1 times minus 1 is minus 1, plus 1 times 2 is 2, that I get 1. Notice this is the identity. And this is actually what I want. If I do m times m inverse, any matrix by its inverse, you get the identity. And likewise, if I do m inverse and I times by m, I will get the identity. So this is a really important idea. This is an idea that basically says, hang on a bit, if I multiply this matrix here by its inverse, effectively it will disappear, because we can think of I as being, the thing that won't change x. So no, I have to be very careful when I put this. 2, 1, 1, 1. I've got to multiply on the right hand side. And I know my inverse now. I've calculated my inverse is this thing here. That's my inverse. So I'm not going to calculate it again. I'm just going to times it 1 minus 1 minus 1, 2. And notice I've times this on the right. I said that I times this left hand side x2, 1, 1, 1 on the right hand side by this inverse. And therefore I can do the same on this side. 1, 3, 3, 2. And since I times this one on the right by 1 minus 1 minus 1, 2, I'll do it over here as well. 1 minus 1 minus 1, 2. Now the whole point about this is this times by this is the identity. I saw that up here. So x times by I on the left hand side. And on this side, well, I don't know what this side is. I'm going to have to actually multiply this out. 1, that's 2. You could do it on a calculator, no one would know. Minus 1, that's 6, I think 5. 3 times that is 3. That's minus 2, I think that's 1. Minus 3, I think that's 1 as well. I don't know if that's right, but now the whole point is xi is really just x. So I could write therefore x equals 2, 5, 1, 1. And I think that's the answer. Let's see what I've got as an answer. Oh, I've got minus 2. Is it just a silly mistake that? Oh, yes, it is. It is a silly mistake because 1 times 3. 1 times 1 is 1 minus 3. I'm not even sure if I might have even said it. But that is the answer. Let's do the second one. It's the same trick, really. Now, on this one, I've got 2, 1, 1, 1. It's actually the same thing. But notice it's on the left now. And we know the order in which you do these multiplications matters. So I want the same thing. I want to effectively move that over there. I can't move it over there. I have to times it by something. So I times it by its inverse. So I got this 2, 1, 1, 1 times by x equal to this. And I'm going to times it on the left hand side. I'm going to chuck it in here. And the inverse of this matrix we've already seen twice now is minus 1, 1 minus 1 minus 1, 2. Times by the 2, 1, 1 on x. Now notice, because I times on the left there, I've got to times on the left here. Last time I times on the right, so I times on the right. So you've got to do the same to both sides. So this time, I'm going to times both sides by 1 minus 1 minus 1, 2. And I'm going to times by, this time it's 1, 3, 3, 2. And of course, the whole point about this, that times by that gives me I. You can think of it almost cancelling out. I work out the right hand side. 1 times 1 is 1. Let's try not to make a mistake this time. That's minus 2. Is it minus 2 again? Oh, alright. 1 times by 3 is 3. Minus 1 times 2 is 1. Minus 1 is minus 1 plus 6. I think that is 5. So they're very similar numbers actually to those up there. Minus 1 times that is minus 3. We get a 4 from that, which gives me 1. In fact, they are all the same numbers, but they're just in a different order. In fact, I think you can easily see when I write x is, I'll write it properly, because obviously I times x is still x. You can see one is the transposed version of the other. They're the same along that diagonal, but these are swapped places. Is that right? Yeah, that's right. So there's my answer. There's my answer again. Yes, it's worked. It's switched round. I'm going to show you this in lesson. There's something for us to do there, and I think that's a good place to stop. I suppose what I want you to remember is this. This rule I've got here, m times its inverse is the identity, or m inverse times m is its identity as well. And in this lesson we're going to do a lot of work on just playing around with matrices and inverses and seeing how far we can get with them. So I hope that makes sense, and we'll call it quits there.